All right, Bram.
To share my screen. Let's see. This one.
We still don't see anything.
No, I know, because I haven't pushed any button. I think I need to. There we are.
There we go. Yep.
Yeah. So that was that. Okay. Shall I start then?
Yes, please.
All right. Welcome to this, last talk of this very interesting week. And of course, we will have a discussion afterwards. So this is a talk about groupoid C-star algebras and topological faces. It will be fairly mathematical. Also, I will be mainly, or only in this talk, be discussing single particle gapped systems. So from that kind of physical perspective, there may be not much new. But I hope that in the discussion afterwards, we can actually see with the formalism that this talk gives us what we can do next. So this talk is mainly based on joint work with Chris Byrne a few years ago in the paper you mentioned, you see here, and it's relevant for some work in progress that I'm doing with Emil at the moment, which is more towards the interacting setting. So as said, maybe we can, maybe there's room in the discussion to talk a bit about that. All right, so I'm going to be talking about groupoid C-star algebras associated to the Delaunay sets and how the K-theory of those recovers some Chern number formulas. And mathematically, a Delaunay set is, we want to think about a point pattern in some Euclidean space, and we model this mathematically by a Delaunay set, which is a uniformly discrete and relatively dense subset of RD. Oh, so feedback. I can hear myself. And on such a Delaunay set, we consider a Hamiltonian on the little L2 space of that set. So the point pattern gives us, the point pattern gives us a little L2 space, just a discrete Hilbert space, and a Hamiltonian will be a strong limit of operators of this form over here. And if we rewrite that a little bit, making the indices dependent by looking at its action on an element in little L2 space, then it takes this form over here. And our goal is to identify these Hamiltonians as elements in a C-star algebra canonically associated to L, and that C-star algebra should be sufficiently small so that it has interesting K-theory, so that we have a chance to recover invariance of this Hamiltonian through non-commutative geometry. And the important assumption here is that we do not assume any translational symmetry for this lattice L, which makes it harder to keep the algebra small, so to speak, because you could imagine if you take ZD as a lattice, you could look at a group algebra associated to that if you would want to. But if there is no internal structure in L, then writing down a C-star algebra becomes a slightly more non-trivial problem. So what we're going to do is we're going to first enlarge the lattice by just adding all its RD translates. So just throw them in a set. And this can be given a decent topology. It's called the hull of L, and that hull has the property that it actually admits an RD action because we've made it that way. And now the Galilean invariance that you want to impose because you're doing physics sort of philosophically leads you to considering the quotient space of this space omega L by RD, by this action. But that quotient space is not well defined because the action can have very wild orbits. And so we say that this is a non-commutative quotient. And it will become clear what this term means in a bit, I hope. And so the proposal is to study it through groupoids. Instead of taking the quotient as such, we associate an algebraic structure to it in the form of a groupoid, and that turns out to give us what we want in a certain way.
Excuse me, I have a question. So how do you think about L and especially omega? So is omega, so L is just a subset of Euclidean space.
Mm-hmm.
So I think it is a discrete metric space or something like that.
Well, I think of L as a point measure, really. So yeah, you think of this as discrete metric space, but it induces a point measure on the functions on RD. Okay. And that's where you, that space carries a weak star topology. So then you can look at the translates inside this space of measures, and that's how you can topologize omega. And so omega consists of all the translates of a fixed lattice L. And that's not a discrete space anymore then.
Okay. So, okay, thank you.
So let's go to groupoids. Okay, this is not a very welcoming slide, and don't worry too much about it if you don't like this technical definition here, because I'm not going to really be working with it, but there may be some people in the audience that are familiar with this structure. There are several ways to define groupoids. One way is saying it's a small category in which all morphisms are invertible. Another more down-to-earth way is the list in this definition. And another informal way of thinking of a groupoid is to say that you have a group, but you cannot compose all elements in this group. So there is a restriction on being able to compose elements, and the restriction is in the categorical picture saying, okay, the range and the source of two given elements have to match up, and then you can compose them. And that's is set here. So there is a range map and a source map on the groupoid, and the set G2 consists exactly of these composable elements. So this is an abstract mathematical structure, but you can actually see them in nature. They're quite prevalent. So a useful thing about groupoids is that indeed they are a generalization of groups, but they're also a generalization of spaces in a certain way. So if I have a locally compact space, then there is a groupoid associated to that, and that's just the space itself. And this groupoid is boring in the sense that no two different elements, no two distinct elements are composable. So the range and the source are just the identity maps, but they will never match up unless you try to compose an element with itself. So not much interesting algebraic structure there, but if you have a topology present, then this is still a useful way to look at it. Then, of course, locally compact groups, the second example, and that's the other extreme. So there, the range and source maps both map to a point, so all elements are composable, and such a groupoid is the composition is determined by the group operation. I wrote here it's étale, even only if it's discrete, but the topological setting will come on the next slide. Sorry for that. there it goes. We will get back to that. Now, an equivalence relation can also be made into a groupoid by looking at its graph, and then the axioms for an equivalence relation translate directly into the right composition properties for a groupoid. So symmetry and transitivity allow you to make a groupoid structure. And this means that you can use any old equivalence relation here. And for example, if you have a group acting somewhere on a set or on a space, then you get an equivalence relation given by the orbits of the action. That's one example, but it doesn't have to come from such a nice geometric setting. So that's the next example at the bottom here. If I have a group acting on a space, then I can also make the Cartesian product into a groupoid by incorporating the action in both the source map and in the composition and inversion. And that's a special case of the example above, and it's a combination of the first two. To Delone is that
Bram, since we are here, could you quickly remind the fundamental groupoid of a topological space? Might be relevant. If you don't derail you too much.
Well, I mean, so you can.
But don't worry, maybe we leave it on the discussion if you don't.
I'm happy to describe it maybe in the discussion. Maybe that's
okay.
That's more well, but I can say it in words. Maybe let me know. Right. Yeah. So if you have a topological space and you want to construct a fundamental group, then you have the restriction that you want to look at loops that start at a given base point. If you let go of that restriction and you look at curves in the space that have different start and ending points, then of course you can compose these if the start and ending points match up, and that gives you exactly a groupoid structure again. And this is the fundamental groupoid of a space, where then if you restrict to a given point, you simply say, okay, I look at those curves that have the same beginning and end point. These are the loops, and then you get the fundamental group. But yeah, we can maybe go into this a bit more later, no problem. So I mentioned already that these groupoids, like groups, they can carry a topology. We want the topology to be nice in some way, so locally compact, Hausdorff, and all these structural maps to be continuous. And a special role is played by the étale groupoids, and those are the groupoids for which the range map is a local homeomorphism. So that means, so if I have G here, then locally an étale groupoid looks like this. This is G0. And the range map goes down here. And so it says that every point has a neighborhood which has an inverse image under the range map that is that looks exactly like the units downstairs. The étale groupoids are important because they are a generalization of the discrete groups. So they are not discrete as topological spaces. There is some non-trivial topology, but they have this pancake structure over here in the picture, which makes them discrete in their fibers, so to speak. So groupoids have there's a rich algebraic theory interplaying with topology and also with analysis, and you can build a whole formalism where you can make groupoids act on spaces. There are co-cycles and cohomology groups, and as we will see, they also admit convolution algebras and K-theory invariants. This is another long definition here that I am going to mainly ignore. This definition describes how you let a group act on a space, and this definition is complicated because unlike a group action, you need to take into account the fact that not all elements in the groupoid are composable, and so they cannot act on any given element of the space. You need a map that relates your space you want to act on to the units in the groupoid. And you can see that if your groupoid is a group, then that space G0 is just a point. So this map becomes redundant. And if you have a non-trivial groupoid, then that's an important aspect. Again, we won't need any of these details, so I'm going to just move on. The properties of group actions sort of carry over. So any groupoid acts on itself from the left and from the right through its category structure. So you can compose arrows. So that gives you group action. You can also make it act on its own unit space by using the range and the source maps. And this is another important way in which groupoids act. So if I have an element in my base space and an element in my groupoid, I can make it act by composing and then mapping it to the range of the element that I get. And in this way, like groups, groupoids induce a dynamical system on their own unit space. And in the case of that transformation groupoid that came already from a group action, this action exactly recovers the group action you started with. So it's really a generalization. And in that sense, you can say, okay, groupoids are also induce dynamical systems on their unit space. So that's what we want to take with us from that. There's a notion of equivalence of groupoids. This also uses this notion of action. And again, I want to think about this somewhat informally. So we say that a space Z is an equivalence between two groupoids if there are commuting left and right actions, so that the quotient spaces relate to the unit spaces in the way that if I take the quotient space of the G action from the left, I find exactly the units of the right groupoid, and vice versa. If I take the quotient space from the right, I find the units of the left groupoid. And an example that's relevant there is if I have a locally compact group acting freely and properly on some space, then I have a nice quotient space. So that's again locally compact in Hausdorff. That gives me a trivial groupoid. And the space I started with, the covering space of this X mod gamma, is acted upon by the quotient in a trivial way because it's a trivial groupoid. And on the other side, the cross product groupoid that I can build from the action acts. And that setup exactly satisfies these axioms. And it gives me a groupoid equivalence between the nice quotient space that I get from the action and this action groupoid. And the equivalence of groupoids is a nice equivalence relation, and these objects are really, in some sense, the same. The upshot of this is that I can also look at actions for which this quotient object is not defined. The action groupoid will be always defined, and therefore it's a substitute of the quotient space, the action groupoid here. And that also fits together again with a groupoid acting on its own unit space, where then the groupoid becomes the substitute for the quotient space of that action. Okay, then there is the whole theory of transversals, which is important when you want to compare two groupoids. And it basically says that they have the same quotient space. So we will see an example of such a transversal coming from a Delaunay set, because we have the hull, which consisted of all translates, but we want to make that slightly smaller and look only at translates by elements of L itself. So an abstract transversal is a subspace of the unit space that meets every orbit and has some favorable topological property in the sense that the range and source maps are open maps when restricted to this subspace over here. And the reason I'm giving you this definition is because this is a way really to generate equivalence of groupoids. The étale groupoids that I singled out are the discrete objects in this groupoid world, and they're also from a computational perspective more favorable to work with. So what we will see is that often you get equivalences from some continuous groupoid with an étale groupoid, where you can compute in a more convenient way usually. So let's go back to our Delaunay set example, where we had the hull and the action of RD. And the action gives us one of these continuous action groupoids. It's a continuous groupoid because RD is a locally compact group. So the fibers of this range map in this groupoid are identifiable with RD. And as I already said in words, we want to look at one of these abstract transversals, which is, in this case, reduces to the transversal of the Delaunay set, where we look at those elements in the hull for which 0 is again in omega. And if you think about that for a minute, then you look at translates of L by vectors x in RD, where the translation needs to happen with an element of L. That's this condition over here. And so if you would look at, say, Z2 in R2, it's a very symmetric lattice, then this transversal is homeomorphic to a torus, because these are the translates that parameterize this omega naught. And from that, we can then build a smaller groupoid. So instead of omega L cross RD, we now look at this groupoid over here. I wanted to label this with L. That will happen later. And this consists of pairs where we take an element in the transversal and an element in that lattice itself. This becomes an étale groupoid by construction. I will not go into details, but you can identify, in this case, the fibers of the range and source maps with the lattice L itself again. And also that by the general theory that I skimmed over before, there is a groupoid equivalence between this continuous cross product and this discrete étale groupoid GL. And the groupoid GL is where our Hamiltonians will reside. So if we recall the expression for a Hamiltonian on L2 of L, then the coefficients in this series representation can be viewed as a map from the transversal groupoid to the complex numbers, because it associates to a translate of the lattice and a point there, this number here, because in this formula for the Hamiltonian, you see exactly occurring the translate of a lattice L by an element in L itself again. Thus, from looking at these Hamiltonians, without going into analysis and convergence, we are led to study the function space. I'm saying here compactly supported functions on G will be slightly bigger, but this will be our relevant space that we want to construct a C-star algebra out of. And for that, we need some more data. And again, this will be a technical definition. We will not dwell on it too much, but we need some notion of Haar measure on a groupoid. So if you have a locally compact group, then you can construct from it a convolution algebra using the Haar measure on the group. For groupoids, you need a system of measures parameterized by its unit space again. So that unit space is all over the place when you work with these things. And there need to be some translation and continuity properties. So now we will see another desirable property when you're étale, because when you're étale, the fibers over a point under the range map are discrete, and so there is always a counting measure there, and those counting measures automatically satisfy the axioms of a Haar system. The other example where this is easy to understand is the transformation groupoid of an action of a locally compact group. There, the fibers of the range map can be identified with G, and there you take the Haar measure on G, it gives you one of these Haar systems. So it's really a generalization of that. And then now you're in the realm where you can start constructing a C-star algebra. So I'm introducing here some extra data, which is that of a 2-co cycle, which I will not define, but in physical settings, they arise from things like magnetic fields, and they twist our products. Again, this is to account for the kind of Hamiltonians that we want. So if we have a G with a Haar system, then we can make CC of G, the space that we were interested in, into a star algebra by the operations I've written down here. And there is also the analog of an L2 inner product, because if I have a measure on a space, I can look at the L2 inner product. If I have one of these Haar systems, I have a family of measures parametrized by a second space. I get an inner product that takes values in functions, again, on G0, which in our case is the transversal. And if G is étale, then these integrals are sums, and the convolution product, for example, takes this form over here, where now you see we are getting closer to the form of our Hamiltonians. And again, the hull with the RD action is an example of a continuous groupoid in which you would have these an actual Haar system, which is not discrete. Now, we saw on the previous slide an inner product with values in this algebra C0 of G0. That's a commutative C-star algebra. And so this inner product structure induces another familiar notion from operator algebras, which is that of a Hilbert C-star module, and that is exactly a right module with a B-valued inner product. There is a natural space of operators on those modules, and they form again a C-star algebra, and they're the analog of the bounded operators on the Hilbert space. Now, because I had that inner product coming from the integrals on the groupoid, I obtain a C-star module completion of CC of G by completing it in the norm given here. And the convolution formulas give you the regular representation on that module, really like in the case of a group. But now, because the operators on this module form a C-star algebra, there is in particular a nice norm, and you can close the norm of CCG to construct the twisted reduced groupoid C-star algebra. And note that in the completion, I'm now also taking the sigma with me. That's because all these algebras start from the same dense subspace CC of G, but the representation on the module coming from the Haar system changes. So that's how we make our C-star algebra. And C-star algebra, so I talked about equivalence of groupoids before. There is a similar relation, or there is a corresponding relation, I should say, on C-star algebras. So Morita equivalence of C-star algebras, the easiest, or the most algebraic example is that of the algebra itself and the matrices over the algebra. So that's the second example in the list here. And they form equivalent C-star algebras. Also, the complex numbers, very small algebra, is Morita equivalent to the compact operators on a Hilbert space H. And to tie up with the examples we saw before, if we have a group acting freely and properly, then the space of functions on the quotient and the cross product, which is the groupoid C-star algebra of the cross product groupoid, they are also Morita equivalent. So it is not unreasonable to expect that there is some link between equivalence of groupoids and equivalence of C-star algebras. Well, that has been extensively studied. So Mully-Renault-Williams proved that if you have equivalent groupoids, you get equivalent C-star algebras. If you take a twist with a 2-co cycle into account, it becomes a bit more delicate. Chris and I looked at this in some detail, and we were confident that you can do this for transversals if they behave nicely with respect to the given cocycle. More generally, the theory would require some more work. I'm actually not sure where this holds, to what extent this then holds. But for the cases we're interested in, the twisted groupoid C-star algebras are also Morita equivalent in case the groupoids are. And so we get equivalences between the twisted cross product of the hull with the group RD and also with this transversal groupoid. And Morita equivalence implies that these C-star algebras have the same K-theory. Okay, so now we're ready to link this to some topological phases and things relevant to the meeting this week. So we consider a Delaunay set, just one. And we assume also given Hamiltonian. So I'm recalling here the structures I've talked about. So we have the hull, we have the transversal, and we have the transversal groupoid. And then the extraneous data of a 2 cocycle. Now, it turns out that the Hamiltonians we are interested in always define elements in the twisted groupoid C-star algebra. This, I think, goes back to Pelissard and Kellendonk, if I'm correct. In any case, it's been observed by many people, that's the proposition below here, that if you have such a Hamiltonian and it has a gap, then it defines a class in K0, and if it has some extra symmetries, then it defines a class in the K1 group of this twisted groupoid C-star algebra. So that's where our motivation for these constructions ends, so to speak. So we found a C-star algebra that contains the Hamiltonians we're interested in. And on top of that, I haven't said anything about the K-theory of this algebra, but the K-theory of the C-star algebra, because it's Morita equivalent to the continuous cross product, is actually the same as the K-theory of the hull omega L. So the topological K-theory of that. And so we can expect that this group is not too large. Okay, so now if we want to compute K-theoretic invariance, we need some further machinery, and this also has come by already this week. So we are going to look at Kasparov-KK theory. And Kasparov-KK theory is a generalization of K-theory where, so Johannes already described this briefly, there is a group KKAB depending on 2 C-star algebras, and in a nice functorial way, in such a way that if you insert the complex numbers in either slot, you get the K-theory or the dual theory K-homology. And there is an associative bilinear product that allows you to move between different KK groups. This product has all kinds of nice properties, which I will not go into. And in particular, it recovers the index pairing. So it recovers the pairing between the K-theory and the K-homology of A. Through the Kasparov product, you see that from eating away the middle variable here, that when you do it in this setting, you end up in KKCC. That's just the K-theory of C that is Z. And if you carefully trace this, you see that you obtain exactly the index pairing. Another way of thinking of KK theory is that an element X in a KK group defines a map between the K theory of A and the K theory of B through the Kasparov product.
Bram, since it came up so many times, can you remind us how it behaves under tensor products?
What kind of tensor products?
So at least is the Kasparov product when you take tensor products with the algebra D.
You mean an X? So I'm not sure if you mean something like this or just the Kasparov product itself.
So it's a B, tensor D.
No, tensor C, there is some third algebra here.
Yeah, that's right.
But what do you mean how it behaves under tensor products?
Is there a statement or statements that can be said about how this structure behaves under the tensor product?
Yes,
Don't worry, I thought it's
I think there are Kunet type formulas and so on. There must be.
I know for sure Nigel has a,
yeah, there must
maybe
be
in his
people in the
thesis
audience
he figured out
but we can, again, this sounds like a good topic for the discussion session.
yeah,
actually. So I think for what I want to say now, there's this categorical structure, you define maps, and the other way. So in the end, I want to get from K-theory some numerical invariants that encode topological faces in some settings. So another important ingredient there is that if you have a trace on the algebra B, then actually that induces a functional on the K-theory. So that tells us that if we have an element in the K-theory of A, just write this, so K-theory of A is exactly this group. So if I pair it with something in a KK group and I land in a second algebra, whatever it may be, where I happen to have a trace, then I can get numerical invariance from this K-theory group. And that's the structure we're going to see in the Delaunay set topological phase setting. So let me say something brief about the Kasparov product, because it's a very intricate theory. But cycles for KK theory are given by pairs of a C star bimodule X and some differential type operator. So that's abstractly meant, and we will see in the example that it is really often that. And these operators can be unbounded. So you can really work with a differential type operator. And in that setting, modulo all kinds of analytic subtleties, the Kasparov product is a generalized tensor product, as is stated in this theorem over here, where the only thing I want to say about this is that if you take Kasparov product, then you have the resulting operator. You can think of that as being composed of the given two operators, which are put together in a sort of orthogonal way. So they have you have two directions in which you have a differential operator, and you put them together as you would do in geometry. And that's the moral of the Kasparov product, I would say. And this will come in when we look at the boundary correspondence. But the recipe to get numerical invariance from KK theory or from a K-theory group can be now directly applied. So if we have a gapped Hamiltonian, then we have a class over here. And we could, if we would have something in this bivariant group and something on the transversal, which is a commutative C-star algebra, then this recipe would apply. Now, the something on the transversal is given in the form of a translation invariant measure. This is data that is often available, and if you have such a measure, then you can build one of these traces and you get this map. So this map is not really hard to get your hands on, but the middle group here, so this is an actual KK group involving a groupoid algebra and the continuous functions on its unit space, which we'd seen before, which always, when you work with a groupoid, this unit space is always floating around as some kind of parametrization space. And it turns out that for the lone groupoid, we can actually obtain a very natural element in this KK group in the middle here. And it comes from the position operators on the groupoid. So, because the groupoid is built from pairs of elements in the transversal and vectors in RD. So we just have coordinate functions on this groupoid. And we can piece them together as we would do in spin geometry by building a Dirac type operator from them. So for that we need some Clifford matrices, Pauli matrices, and if you take the operator here, which is really the analog of a Dirac operator, then you find actually that you get one of these KK theory elements in this group. So the direction it differentiates in are really the groupoid directions, and then it's parametrized over omega. It's a field of differential operators over this omega naught, even though none of these structures here have to be manifolds. The formalism is analogous, but the applicability is much wider. And this element gives us a map from the degree D K theory of the algebra that contains our Hamiltonians to the parameter space that our groupoid was defined over. Combined with an invariant measure, we then get numerically valued maps on this K-theory group. Now, to say something more about the measures, there is a one-to-one correspondence between invariant measures that are invariant on the RD action under the full hole and measures on the transversal that are invariant under the action of the étale groupoid. And such measures then induce a trace on the entire groupoid algebra. And Emil and Chris proved the following result, that if the measure on omega L is ergodic, then the corresponding trace, so there's another measure on omega naught, then the corresponding trace can be actually computed by the limiting procedure stated in this proposition, where we approximate the lattice from finite sets. So we approximate it by making it bigger and bigger, and this makes this trace computable. So that brings us to the main result about these Delone groupoids. If we now compute our composition, so we take a class of a gapped Hamiltonian in the K-theory group of C star G sigma, we take the Kasparov product with our preferred element. So that's this class D here of this Dirac type operator. It's kind of fundamental class. And then you really recover Chern number type formulas from these unitaries and this measure. These are the formulas over here. So they're really expressed in terms of the nice algebraic data that we have. So the position operators feature here, and they just feature as derivations because we're taking commutators. And this computes an index type pairing, and they give us the familiar formulas where also the approximation trace features in this second component. Now, before I finish, I will briefly say something about the bulk boundary correspondence. If we want to make an edge cut in our material, then we are going to fix the last coordinate of our lattice, and if we do that algebraically, what we obtain is a subgroupoid, which I call H over here, and we can look at its groupoid C-star algebra. And by isolating the coordinate that we are making constant, namely 0, we again get one of these position operators, but now the position operator only acts in the D direction, so in the direction of the cut. And that gives you another KK cycle, and it gives us a KK cycle in the group over here from the big algebra to the small algebra. So that gives us a map from the d-dimensional K-theory of the, say, bulk to the d-1 dimensional K-theory, the boundary algebra. And that boundary algebra, of course, itself has one of these fundamental cycles because there are d-1 position operators left to play with. And that assembles nicely in exactly the same way to one of these fundamental cycles. And then if you take at heart this philosophy that the Kasparov product is really just a tensor product, then what we've done is we had our operator d case 1. Operator d, and what we've done is we've chopped off the last coordinate, and we can now put that together with the operator for the boundary, which has one coordinate less already. We add them up, and that recovers the operator we started with. So that idea really encodes the bulk boundary correspondence. So there is a map from the K-theory of G to the K-theory of the small algebra, and the diagram using the fundamental cycles, it commutes. So K-theoretic invariants of the big algebra have corresponding K-theoretic invariants of the small algebra. And it doesn't matter in which order you compute those, you will get the same answer. Okay, I think we're almost through. Yes, this is the summary. So from any Delone set, we can build an Untitled groupoid, and that groupoid contains the Hamiltonians we want, the defined K-theory elements. There is always a natural fundamental class in the KK group, parameterized by the transversal. And using an invariant measure, we can compute the K-theoretic invariants, and they recover the Chern-type formulas that we saw. Plus, we can also formulate the bulk boundary correspondence in a completely natural way in the setting. And that's where my last comment on the work in progress that I'm doing with Emil at the moment is to build a groupoid for the interacting setting, where instead of, so the groupoid of the Delone set that we looked at had an element in the transversal and a fixed element in the set. The idea we're pursuing is to actually single out n different points in the set, but there are many things happen when you start doing that, let me say it like that. And with that, I will thank you for your attention and for the very interesting week already, even though we have a discussion session to come still. Thank you.